Okay, welcome. This is Dr. Morton. This is the Logic Design video, which is class day number 19, and we're going to talk about chapter 10. This is a pretty exciting topic because we're going to jump into the very beginnings of our sequential design by introducing flip-flops today. Now, we are going to put flip-flops on the next test, but really flip-flops are our sequential design element that allows us to build state machines. And we use the flip-flops to hold the number of the state that we're in. So we're going to talk about how we develop devices that have memory. And it turns out that memory is really a feature of devices that we use to incorporate to incorporate feedback to give us stable states. In this case, two stable states. And so the first thing I'm going to do is show you how this works. But let's talk a little bit about. Let's see. Let's look at the syllabus. I'm having trouble thinking of my words here. Okay, we'll look at the syllabus, and then in a minute we'll look at the slides. All right, so this is October the 7th. Although I'm recording it on the 9th, I'm doing it on Sunday. We had 20 people over for dinner Friday night, medical students and dental students, and actually some residents and even some people who finished residency. In fact, one person in fellowship, one person out. Okay, well anyway, so what we're going to do is we're going to cover chapter 10. And then you were supposed to turn in your truth tables for your projects, so hopefully everybody did that. If you didn't, go ahead and get them turned in as soon as you can. You can turn them in late. It's not going to count points off, but I do want you to, it's critical to start making progress on your projects. All right, and then we will be presenting the projects not next week, but the following week, starting October 17th. And we probably won't take all week because we only have 4 groups, so we'll maybe only take a couple of days. And then we'll talk about finish flip-flops up on Monday, and then we'll start reviewing for the test. Then we'll do the group presentations and a little more test review, and then the midterm test on October 26th. All right, so with that, let's look at the slides. Okay, and let's see. I think these transition correctly. All right, so the learning objectives. So I want you to understand how a set reset latch can have 2 stable states using feedback, and we're going to make that set reset latch out of 2 NOR gates, and I'll show you about that in just a minute. And I'll also play a little video clip with that. Yeah. Secondly, I want you to be able to explain how an edge-triggered JK flip-flop can be made from 2 SR latches. And I want you to be able to describe 2 primary uses for flip-flops. And then I want you to be able to list the primary differences between JK, T, and D flip-flops and explain the differences between a latch and a flip-flop. Now, for the last one, the difference between a latch and a flip-flop is that a latch generally does not have a clock and a flip-flop does. And it's usually an edge-triggered clock. And we'll learn all about that hopefully in the next few minutes. All right. So these are the things we're going to cover. And we're going to start with the SR latch. But I already did sort of mention this. These latches and flip-flops have 2 stable states typically. The states can be changed by their inputs, but the state will stay the same if there's no change in the inputs in general, although you can have a flip-flop set up to toggle each time. So these are sequential networks that we're going to study in the last third of the course, require memory to hold what state we're in, and we're going to use flip-flops for that. All right. So again, both latches and flip-flops can hold 1 bit, either 1 or 0, which means true or false. Set or reset sometimes, or set or clear. We use those terms as well. Or sometimes we use the terms preset and clear. Both have 1 or 2 inputs, and one or two outputs. Usually the outputs are the complementary Q and Q prime, where Q and Q prime are always the inverse of each other. So if the flip-flop is set, Q will be a 1, Q prime a 0. If the flip-flop is clear, Q will be 0 and Q prime will be a 1. A latch generally has no clock. A flip-flop generally has a clock and changes states when allowed to by the clock. Our clocks can be edge trigger clocks or level clocks. And what makes this important is that most of the time we use edge trigger clocks, and we get that by using a master-slave arrangement. We'll cover that in just a little bit. But there is such a thing as flip-flops with level clocks. In a level clock, as long as the clock is high, then the inputs can change the outputs. In an edge trigger clock, the inputs set up a master stage, and then when the edge, when the active edge comes, which could be a rising edge or a falling edge, depending on which type of flip-flop it is, then the slave stage, the output part of the flip-flop, then changes to the correct next state. Okay, all latches and flip-flops involve feedback to make them work. And we send the outputs back to the inputs in some way, and that's what gives them these stable states, and also it makes them more robust because we prevent illegal states. All right, which are these forbidden input combinations. All right, so here's our basic set reset latch. And if you look at this, you see we have two NOR gates. It's just a standard OR gate with a bubble on the output. Same thing down here. And normally the way I like to think about this is I figure out what the output of the OR gate is before the bubble, and then I just flip it, and then we talk about the output after the bubble. All right. Now in this case, we have two inputs, an S input, which stands for set, and an R input, which stands for reset. And here's our sort of our truth table, or you might say more appropriately a state table, because this actually involves the concept of time. So so S and R are our two inputs, and if they're both 0, which one of the stable states this flip-flop this latch is in, it will stay in that state. On the other hand, if S is 0 and R is 1, then the latch will go to a cleared state where the output Q is 0 and Q prime would be 1. If S is 1 and R is 0, just the opposite. Q becomes 1, so we say the latch is set, and Q prime becomes 0. Now what's forbidden is for S and R to be 1 at the same time, and we'll show why this is true. And this is mostly because we have this concept of it's an unstable state, and it also can oscillate and create all sorts of problems. And then if you take S and R away, you don't know which state it's going to resolve to. So those are all problematic. So we normally say for an SR latch, this is our equation. Our next Q is going to be S ORed with R prime Q, the current state of the flip-flop, of the latch rather, given that S and R are not both 1. So SR has to equal 0. So one of these has to be 0, or both. But they can't both be 1 and be equal to 0. So S ANDed with R has to be 0. Okay, so let me show this little YouTube video. So let's see. Hang on while I get this set up. Okay, so here's our SR latch. I'm showing this in Logisim. You can see that this is this is what the Logisim logic simulator looks like. And so what's going on here, I have two NOR gates I've set up, and I've put feedback for both of them are 2 input NOR gates, and I have the output of one going into the input of the other, and vice versa. And I have 2 outputs, Q prime and Q. I have 2 inputs, S and R. Now, unfortunately, I can only punch one button at a time, but I'm going to show you at the end what happens when you punch both buttons by connecting them just to be one button together. All right, so so it starts off like this, and then when I run the simulation, I'm going to go in and I'm going to click the poke button here. And now that I have the poke button, so first thing I'm going to do is I'm going to punch the reset button. When I punch reset, notice Q is 0, but I've turned on the Q prime LED. So Q prime is 1, Q is 0. The light green shows where the 1s are, and the dark green shows where the 0s are. Notice that these are dark, so these are 0s. When I'm holding it, notice it's light green, so it becomes a 1 while I hold the button, and then it goes back dark when I let the button go. Now, the way this works, when I just boot it up, let's say I just power this thing up, and as they come up, this one maybe is seeing 2 zeros, so it starts to do a 1 before the before the bubble and a 0 after, and it feeds that 0 back here, and you have a 0 going in, and this is a 0, so now you have a 0 before the bubble and a 1 after, and the 1 comes in here, and now you have a 1. You have a 1 before the bubble and a 0 after, and so it settles into this stable state. And this output here is driving this with a 0, forcing a 1 before the forcing a 0 before the bubble and a 1 after, and this 1 is forcing a 1 before the bubble and a 0 after here. So this is a stable state. Now if I punch the S button, notice it switches. Now the Q is lit, Q prime is 0, so Q is 1. And now we have, when I let go of the button, well, that should go dark, and it doesn't. That's interesting. But anyway, so we have the S is theoretically a 0 here, but the 1 is feeding back from this NOR gate, and it's driving a 1 before the bubble and a 0 after, and this 0 is feeding in here and driving a 0 before the bubble and a 1 after. Okay, and so then if I hit the S again, shouldn't really change anything, but if I hit the R, yeah, see, this is goofed up. We have a problem here, Houston. Oh, man. Let me connect it again. All right. Okay, I think I fixed it. I don't know. Something went horribly bad. All right. So here we have the SR latch. So you see, when I punch the button, it is a 1, and when I let go, it's a 0. Same with here. Switches, and they switch back and forth. We have these two stable states. All right, and you should see how we get this by feedback. Now, let me show you what happens if we try and bring them up. If we try and make them both 1 at the same time. So I'm gonna delete this, and I'm gonna delete that, and then I'm gonna use the wiring tool, and we're gonna hook this. Now you can see we've got them both here. Now I hope this shows up. We'll see. Oops, wrong thing. I have to get the poke button. All right, now I'm going to poke it. And notice that my Q and my Q prime are both 0 because we're driving both NOR gates to a 1 before the bubble and a 0 after. So Q and Q prime are both 0. Well, that's wrong because they're supposed to be the opposite. And then watch what happens when I let go. Oscillation apparent. So it detects that this is unstable. That's why it's a forbidden state. All right. Okay, so that helps you see, and you can watch this demonstration on this little YouTube link if you want to click it or type it in, I guess. All right. So we can write our how this performs. We can use this simplified little chart here, where we talk about hold, clear, set, and unstable, or we can write our current state of Q and what would be the next state, and we have these don't cares down here because this is S and R both 1, which is illegal, forbidden. Okay. All right. we can change this up a little bit and add AND gates in front of our SR latch. We can have R going in here, S coming in here, and then we have this gate. The gate basically enables or disables both of the AND gates. And when those gates are enabled, then if the gate is a 1, then an R as a 1 can be passed on. R and S as a 1 can be passed on. But if the gate is closed, then R and S can't have any effect on the inputs. The inputs will both be 0. And you can see this has some advantages. You can see that this does not avoid R and S both being 1, though, because, well, it doesn't fix that. We call this a gated SR latch, but we still have to make sure R and S are not 1. Now, we have another thing we can call a D-gated latch. Now, notice here we actually have the inverter on the D input going into the OR input here through this AND gate, and then over here it does not get inverted. And we also have still the gate, and the gate basically shuts off both AND gates or allows them to pass through. Now, if D is a 1, then you'll have a 0 in here and a 1 in here, so the S will be 1 and the R will be 0. If D is a 0, you'll have a 1 going into the R, assuming the gate's a 1, but a 0 coming into the S. So R and S will never be both 1 at the same time with this arrangement. And so that fixes our forbidden state. That's a more robust solution. But we still don't have a clock. We just have a gate here. When the gate is open, that is when it's a 1, then D is passed through to the RS latch. If D is 1, the latch will set. If D is 0, the latch will clear. When the gate is closed, changes in D have no effect. And you can see that here. Gate's closed, D has no effect. Gate's open, and D is passed through with a small propagation delay. Gate is closed, and then it's left in this high state even though D goes away here. So D has no effect. So it's in hold mode. When the gate's closed, the latch is in hold mode. When the gate is open, it follows D with a small propagation delay. All right. Now, a clocked T flip-flop. Here we have a clock, and we bring in some feedback here from the outputs to prevent R and S ever being 1 at the same time. But we have both these inputs tied together. So, but notice only one of these AND gates will ever be turned on because Q prime and Q should always be the opposite. And so this also prevents R and S being 1 at the same time. But what happens then in this case is every clock pulse, this latch will switch from, if it's 0, it'll be set. If it's set, it'll be cleared. And that keeps happening. So it just goes back and forth from 0 to 1. It toggles on every clock pulse. Now, we haven't really talked about this clock or how this is done. We'll really come back to this later. All right. And I'm not going to talk about this. What I do want to talk about is this master-slave JK flip-flop. And so this is really the mother of all flip-flops. And this is really the way they're pretty much made. And this flip-flop arrangement gives us an edge-triggered clock, and it also makes things a lot more robust. So this protects us from having signals change in such a way to create meta states that can screw up your timing considerably. So the way this works, and here's the timing diagram. I'm not going to talk about this too much. I just want to focus on this. So notice we have an RS latch here called the slave stage. We have an RS latch here called the master stage. This one has two input AND gates on its inputs, R and S. This one has two 3-input AND gates on its inputs. Notice we have feedback from the outputs of the slave stage to the inputs of the master stage, and they're crossed over, which basically means that if this slave stage is outputting, say, Q equals 0, then that'll put a 0 into this K AND gate, and it'll put a 1 into this J AND gate. So it'll prevent R and S from ever being 1 at the same time. Over here, you don't have to do that because this Q and Q prime should never be 1 at the same time, so R and S would never have a problem being 1 at the same time, since they can't be over here. Notice we have a clock input here. In this case, the clock is directly tied to these AND gates, but it goes through an inverter to these AND gates. So at any time these AND gates are enabled by the clock, potentially, these AND gates are disabled by the clock, and vice versa. When these are disabled, these are enabled. What that prevents is changing states other than on the one moment when the clock switches from high to low. When it's high, it allows you to set up the master stage, and then when it transitions to low, it shuts off the inputs, so it puts R and S into a hold mode here for this latch, but it propagates through these AND gates, the Q and Q, the Q prime and the Q, to the R and S terminals. So basically it just propagates however this latch is, this slave latch becomes set the same way, or cleared the same way. However if it's set, it'll be set. If it's clear, it'll be clear. And then this is in hold mode, so these won't change until the clock goes back high and allows the changes. When the clock goes back high, these gates will be shut off so that changes over here won't propagate until the edge triggers it. So it's a very robust setup, and it also guarantees that changes will only occur on in this case the rising edge. Sorry, on the falling edge, when the clock transitions from high to low. That's when these AND gates will be activated and R and S will be put in a hold mode here. All right, hopefully that makes sense. Now, we can take this flip-flop, which we normally represent as a single box. We don't show the internal circuitry. And we can convert that. It'll be a JK, master slave, edge triggered flip-flop. We can convert it into a D flip-flop or a T flip-flop, and we'll talk about that. I'll probably talk about that more next week. This is really the kind of the basics I wanted you to get. Okay, I think that is pretty much what I wanted to cover. So let's see what else we had here. I think, yeah. Yeah, that's pretty much it. Okay, so I'm going to stop here, and I'll post this video, and you can review this, and hopefully this will give you a good sense of how how flip-flops are built and how we get to an edge-triggered JK flip-flop. And then on Monday I'll talk about how we can turn the JK flip-flops into T's and D's. Okay.